For all of human history, it has been there, a silent, silver companion hanging in the velvet darkness of the night sky. We have gazed upon it, written poems about it, woven it into our myths and our dreams. The moon is not a strange world. It is our cosmic neighbor, a familiar face that has governed our tides and marked the passing of our months since we first looked up. We have visited it for a few fleeting moments, leaving footprints in its ancient dust before returning to the vibrant blue of home. But what if those visits were not so brief? What if the footprints were not just a symbol of a journey taken, but the first steps toward a life lived? What would it truly be like to call the moon our home? To wake up not to a blue sky, but to a black one, with the earth itself hanging like a giant, swirling marble in the eternal night? The experience would be far more than just low gravity and a lack of air. It would be a profound reshaping of what it means to be human, a life lived on the very edge of reality in a world of magnificent desolation. Tonight, we will make that journey and take the first steps toward that life. Before we begin our final descent, I would love to know where on our home planet you are joining this voyage from. Let me know your city or country in the comments below. And if you enjoy these calm, educational explorations of our universe, consider subscribing. Your support allows us to continue these journeys together, always calmly, always at the rhythm of the universe. Our story begins in the final phase of the transit, as the initial excitement of leaving Earth gives way to the immense reality of the destination ahead. The journey to the moon is not just a crossing of space, but a crossing of a psychological threshold. We are leaving the entire biosphere, the whole of our known world, to enter a realm governed by a completely new set of rules. Let us look through the viewport as our once distant moon grows to become a vast, physical, and formidable landscape. The final approach is a descent into an alien reality. The romantic silvery glow seen from Earth dissolves into a landscape of stark, brutal detail. There is no atmospheric haze to soften the view, no gentle gradient of color. The surface is a monochromatic panorama of grays, whites, and blacks, defined by the unfiltered light of the sun. Craters that appear as gentle smudges through a telescope reveal themselves to be vast, sharp-edged chasms, some many kilometers wide, with floors lost in impenetrable shadow. The lines are crisp, the details absolute. Distant mountains, hundreds of kilometers away, appear as if they are just beyond arm's reach, a visual trick played by the lack of atmosphere. This is a world that has remained unchanged for billions of years, a place without weather, without wind, without any of the dynamic processes that shape our own world. It is a museum of the solar system's violent past, and the lander is now descending into its main gallery. Inside the cabin, the final moments before landing are a study in contrasts. The silence is absolute, broken only by the hum of onboard systems and the calm, measured voices from mission control. A connection to a world now 250,000 miles away. Outside, the lander's engines fire, but no sound penetrates the vacuum. The descent is a silent, controlled fall, a delicate dance of physics and engineering above a surface that offers zero forgiveness. Then, with a final, gentle tremor that resonates through the structure of the craft, the motion stops. The engines cut out, and the silence that follows is deeper and more profound than any that can be experienced on Earth. It is the silence of a world without air, without life, without even the whisper of a breeze. It is the true sound of the void. The first moments on the surface are not spent rushing to the airlock, but in stillness, absorbing the reality of the view from the window. The landscape is utterly static. The sun, a searingly brilliant point of light in the black sky, casts shadows that are not the soft, diffused grays of Earth, but are instead pools of pure, featureless black. The line between light and shadow is as sharp as a razor's edge. To step from sunlight into shadow is to move between two worlds, one of brilliant, glaring heat and one of deep, cryogenic cold. Nothing moves. There is no dust stirred by wind, no clouds scudding across the sky. Every rock and crater rim will remain exactly as it is for millennia, unless disturbed by a meteorite impact or a human presence. It is a vista of perfect geological permanence. But this stark, gray desolation is not the main feature of the view. The true spectacle hangs above the horizon, in the black sky where a blue one ought to be. It is the Earth. From the lunar surface, Earth is not a star or a planet in the familiar sense. It is an astonishingly large, vivid, and dynamic presence. It appears nearly 4 times larger in the lunar sky than the moon does in ours, a disk of impossible color and life. The deep, royal blue of the oceans provides a stunning contrast to the brilliant, swirling white of the cloud systems, which can be seen forming and moving in real time. The familiar shapes of continents are visible, the tan of deserts, the deep green of forests, all rotating slowly in a silent, majestic ballet. To a settler on the moon, Earth is a celestial clock, its 24-hour rotation, a visible and constant process. This is the overview effect, an experience described by astronauts as a profound cognitive shift in awareness. But for a temporary visitor, it is a fleeting revelation. For a permanent resident of the moon, it becomes the fundamental backdrop of their existence. The sight of Earth is a constant source of wonder, a reminder of the beauty and complexity of the world left behind. It is also a source of profound isolation. Every human being who has ever lived, every war ever fought, every piece of art ever created exists on that single fragile sphere hanging in the darkness. It is home, yet it is now unimaginably distant, a paradise of warmth and life, separated by 250,000 miles of weeful, empty space. This view, in all its glory, defines the new reality for a lunar settler. They are not simply on another world looking out at the cosmos. They are on a cosmic lifeboat, forever looking back at the ship they have left behind. The journey is over, but the challenge of comprehending this new perspective has only just begun. Having absorbed the profound, silent view from the viewport, the lunar settler must now confront the physical reality of the world outside. The serene beauty of the landscape is a deceptive veil, hiding an environment more hostile to unprotected life than any on Earth. To exist on the moon is to live inside a bubble of technology, a fragile sanctuary where the rules of our homeworld are meticulously recreated. The first lesson of lunar life is that the boundary between the habitat and the surface is the boundary between life and immediate death. The primary threat is not a creature or a climate, but the very nature of the place itself, beginning with the complete absence of an atmosphere. The lunar surface exists in a near-perfect vacuum, a pressure so low that it is difficult to replicate in even the most advanced chambers on Earth. This is not merely an absence of breathable air. It is an absence of pressure, the gentle, constant weight of an atmosphere that our bodies have evolved within. Without the protection of a pressurized suit or habitat, an unprotected human would face a swift and catastrophic end. The lack of external pressure would cause the liquids in the body to, in essence, boil at body temperature, a gruesome process known as ebullition. The air in the lungs would expand violently, causing fatal trauma. Consciousness would fade in seconds. The vacuum is an absolute and uncompromising barrier to life. This vacuum has profound implications for technology as well. Materials behave differently here. Without an atmosphere to shield them, plastics and composites can release trapped gases, a process called outgassing, which can make them brittle and compromise their structural integrity. In the pristine void, two perfectly clean pieces of the same metal can fuse together on contact with no heat required. A phenomenon called cold welding that poses a constant risk to mechanical parts and docking mechanisms. Furthermore, the lack of air means the lack of a medium to carry sound. The silence experienced upon landing is not just a peaceful quiet, it is a fundamental property of the world. A falling tool, a running rover, even a catastrophic explosion on the surface would be utterly silent to an observer standing just meters away. The lack of atmosphere also means there is no shield. The Earth's sky is a 5-layered blanket that protects us from the harshness of space. On the Moon, that blanket has been stripped away. This leaves the surface exposed to a constant rain of micrometeoroids. While larger impacts are rare, the Moon is continuously bombarded by particles ranging in size from grains of sand to fine dust, traveling at hypervelocities of tens of thousands of kilometers per hour. A particle the size of a pebble, carrying the energy of a speeding truck, could puncture a habitat wall. Even a speck of dust could penetrate a spacesuit with lethal consequences. This creates an environment of constant, unpredictable risk, where the sky, though black and seemingly empty, is a shooting gallery. However, of all the environmental threats on the Moon, the most insidious, pervasive, and challenging is the one that lies underfoot, the lunar regolith. This is not soil or sand as we know it. For billions of years, the surface of the Moon has been pulverized by the relentless bombardment of micrometeoroids, with no wind or water to smooth the resulting particles. The regolith is a blanket of fine, sharp, and abrasive dust that covers the entire lunar surface. The individual grains are like microscopic shards of glass, with jagged edges and a consistency finer than flour. During the Apollo missions, this dust proved to be a formidable adversary. It clung to the astronauts' suits, scratched their helmet visors, and wore down the seals on their equipment. Its abrasive nature means it can grind away at fabrics, metals, and moving parts, causing them to fail. But the true danger of the regolith goes beyond its mechanical properties. Due to the constant stream of charged particles from the sun, known as the solar wind. The dust of a lunar surface is electrostatically charged. This gives it an almost magnetic quality, causing it to levitate slightly above the surface at the terminator line and to cling tenaciously to any object it touches. Cleaning this dust from a spacesuit before re-entering a habitat is a monumental challenge, and failure to do so presents the greatest long-term health risk for lunar settlers. If these fine, sharp particles are brought into the habitat and become airborne, they can be inhaled. The long-term exposure to such dust could lead to severe lung conditions, a lunar version of silicosis, a disease miners on Earth have long contended with. The dust is not just a nuisance. It is a toxic substance. It can irritate the eyes, damage the respiratory system, and contaminate every surface inside the delicate, closed environment of a home. Therefore, the first and most critical architectural challenge for any lunar base is not just building walls, but designing systems, airlocks, decontamination chambers, and surface protocols to conquer the omnipresent threat of the dust. To live on the Moon is to wage a constant war against an enemy as fine as powder and as sharp as glass. To live on the Moon is to solve a series of fundamental survival challenges. The creation of a pressurized, breathable habitat conquers the vacuum. A meticulous strategy for dust mitigation controls the threat of the regolith. Yet, even within the secure walls of a lunar home, invisible dangers persist. These are threats that cannot be seen or felt, but which silently and relentlessly assault both human biology and technology. They are the twin hazards of cosmic radiation and extreme temperatures, a direct consequence of the Moon's lack of a planetary shield. On Earth, we are protected by a dual-layered defense system, a powerful magnetic field that deflects the most energetic particles, and a thick atmosphere that absorbs what remains. The Moon has neither. It is a naked world, fully exposed to the harsh radiation environment of deep space. This constant exposure comes in two distinct forms. The first is a persistent, low-level shower of energy known as galactic cosmic rays, or GCRs. These are not rays in the conventional sense, but physical particles, the nuclei of atoms, primarily protons, but also heavier elements like iron that have been stripped of their electrons and accelerated to nearly the speed of light. They originate from cataclysmic events far outside our solar system, such as supernovae, and travel across the galaxy for millions of years. This means they arrive at the Moon from every direction, creating a constant, isotropic background of radiation. The threat from GCRs is not acute, but chronic and cumulative. These microscopic bullets are so energetic that they can pass straight through a spacesuit, a habitat wall, and the human body itself. As they do, they leave a trail of damage, shattering the molecules they strike, including the delicate strands of DNA within our cells. The body is adept at repairing this damage, but over time, errors can accumulate. For a lunar settler, this translates to a significantly increased lifetime risk of developing cancer, cataracts, and degenerative diseases affecting the heart and central nervous system. There is no hiding from GCRs. The dose simply builds up, day after day, limiting the total amount of time a person can safely spend on the Moon without adequate protection. The second form of radiation is far more violent and immediate. Solar particle events, or SPEs. These occur when the Sun, in a period of intense activity, unleashes a massive burst of energy in the form of a solar flare or a coronal mass ejection. These events flood the surrounding space with a torrent of high-energy protons. Unlike the steady drizzle of GCRs, an SPE is a sudden, unpredictable radiation storm. An unprotected astronaut caught on the lunar surface during a major SPE could receive a massive, potentially lethal dose of radiation in a matter of hours, leading to acute radiation sickness, a devastating illness that damages the body's most sensitive tissues, including bone marrow and the gastrointestinal tract. To survive, lunar habitats must include a dedicated storm shelter, an area with significantly thicker shielding, where the crew can retreat for several days until the solar storm subsides. The only effective defense against this onslaught of high-energy particles is mass. A thick, dense barrier of material must be placed between the settler and the cosmos. While hydrogen-rich materials like water or polyethylene are highly effective on a per-kilogram basis, the sheer quantity required for protection makes launching them from Earth prohibitively expensive. The most practical solution is to use the most abundant material available on the Moon, the regolith itself. This realization fundamentally shapes the entire philosophy of lunar architecture. Open plains habitats, like those often depicted in science fiction, are a dangerous fantasy. Survival on a Moon means going underground. By burying a habitat under several meters of regolith, settlers can use the very ground they live on as a shield, providing the necessary mass to significantly reduce the daily dose from GCRs and offer a safe haven from the fury of a solar storm. This subterranean approach also solves the final environmental challenge, the extreme swings in temperature. Without an atmosphere to trap heat and moderate temperatures, the lunar surface experiences one of the most brutal thermal cycles in the solar system. In the direct, unfiltered sunlight at the lunar equator, the ground can heat up to over 120 degrees Celsius, well above the boiling point of water. but in the darkness of a shadow, or during the 2-week-long lunar night, the temperature plummets to below -170 degrees Celsius. This relentless cycle of extreme heating and cooling induces immense thermal stress on any exposed equipment, causing materials to expand and contract, which can lead to metal fatigue, cracked seals, and structural failure over time. Living underground provides a natural and perfect insulation. Just a few meters below the surface, the temperature of the regolith is a constant, stable cold, protecting the habitat from the wild swings on the surface and making it far easier to maintain a comfortable, steady temperature inside. The lethal environment of the moon, with its vacuum, dust, radiation, and temperature extremes, all points to a single, inescapable conclusion. Humanity's future on the moon must be built not on its surface, but within it. The hostile lunar environment dictates a clear architectural mandate. To survive, humanity must seek shelter beneath the surface. This conclusion, born from the hard realities of radiation, temperature, and micrometeoroid threats, transforms the challenge of lunar settlement from one of mere construction to one of strategic excavation and adaptation. The first lunar architects will be as much geologists and miners as they are engineers. Their work will not be about erecting towers that scrape the black sky, but about carving out safe, livable spaces within the ancient lunar rock. This leads to two primary architectural philosophies: finding and inhabiting natural subterranean voids, or creating new ones from scratch using the very material of the moon itself. The most tantalizing prospect for a ready-made lunar home lies in the moon's volcanic past. Billions of years ago, when the moon was still geologically active, vast rivers of molten lava flowed across its surface. As the top layer of these rivers cooled and solidified, the molten rock beneath continued to flow, eventually draining away and leaving behind immense hollow tunnels. These are known as lava tubes. On Earth, lava tubes are a common feature of volcanic regions, but on the moon, the lower gravity and lack of weathering have allowed them to form on a scale that dwarfs their terrestrial counterparts. Recent data from lunar orbiters has identified several pits, or skylights, which are thought to be collapsed sections of the roof of these massive caverns. These skylights are gateways to potentially colossal underground networks. Once a suitable section is identified, the process of turning a raw cave into a human outpost can begin. The simplest approach would involve lowering large inflatable habitat modules through the skylight. Once on the cavern floor, these modules would be inflated, creating a soft-walled, pressurized clean room protected from the lunar dust. This inner habitat would contain the living quarters, laboratories, and life support systems. The vast, unpressurized space of the lava tube itself could then be used as a sort of cosmic garage, a shirt sleeve but not breathable environment where rovers could be parked and maintained and large equipment could be stored. All without the need for bulky spacesuits, just a simple respirator. Sealing off entire sections of the lava tube with immense custom-built airlocks could eventually allow for the creation of vast pressurized areas, large enough to contain entire towns with parks and agricultural zones, all under the safety of a rock ceiling. However, suitable lava tubes may not exist in the most scientifically interesting or resource-rich locations, such as the water ice-bearing craters at the lunar poles. In these cases, settlers must create their own shelter from the ground up, which brings us to the second major school of lunar architecture, in-situ resource utilization, or ISRU. The core principle of ISRU is simple: don't bring what you can build. The most valuable resource for construction on the moon is the regolith. The same fine, problematic dust that poses a threat to health and machinery can be transformed into a building material of incredible strength. and utility. The leading technology for this process is advanced three-dimensional printing. Robotic systems equipped with powerful lasers or microwave emitters would scoop up scoops of raw regolith. By focusing intense heat onto a thin layer of the dust, the particles can be melted and fused together in a process called sintering. Layer by painstaking layer, the printer can create solid, ceramic-like objects of any desired shape. This method could be used to produce simple interlocking bricks akin to cosmic Legos, which could then be assembled by other robots to form walls, radiation shields, and landing pads. More advanced systems could print entire habitat structures in one continuous process, building up the walls of domes or vaulted ceilings directly on the lunar surface. The initial habitat would likely be a hybrid structure. A lightweight, inflatable pressure vessel brought from Earth would be deployed first. Then, an autonomous 3D printing rover would begin its work, slowly building up a thick, protective shell of sintered regolith over and around the inflatable module. This provides the best of both worlds. The initial habitat is deployed quickly, while the heavy, radiation-shielding mass is sourced locally, saving an immense amount of launch cost and complexity. This additive manufacturing approach allows a settlement to grow organically. As the population expands, new modules can be added and subsequently buried, creating a sprawling, interconnected, subterranean complex. These structures would be incredibly resilient, their thick ceramic walls offering superb insulation and protection. The sources for this recycled water are the settlers themselves. The water vapor in every exhaled breath, the perspiration from every body, the water used for hygiene and cleaning, and most significantly, the water content of urine must all be collected. This collected wastewater is then sent to a water processor, a sophisticated system of purification that mimics and accelerates the Earth's natural water cycle. The process begins with filtration to remove solid particles. Following this, the water undergoes a process like vapor compression distillation. It is heated into a vapor, leaving salts, minerals, and other non-volatile contaminants behind. This purified steam is then recondensed back into liquid water. The final stage is often a catalytic oxidation reactor, which uses high temperatures to break down any remaining organic compounds, ensuring the final product is often purer than the tap water in most cities on Earth. Life would be lived in these buried warrens, connected by tunnels, with surface access limited to heavily shielded airlocks for excursions in rovers and spacesuits. Whether we choose to inhabit the grand, natural cathedrals of the lava tubes, or construct our own bespoke shelters from the lunar dust, the architectural language of the moon will be one of mass, depth, and defense. It will be a civilization built not in defiance of the sky, but in retreat from it. Within the shielded, subterranean architecture of a lunar home, settlers are protected from the harsh realities of the cosmos. But this physical shell, this barrier of rock and regolith, is only the first layer of survival. The true challenge of living on the moon is not keeping the universe out, but creating a complete, functioning world within. The habitat is not merely a shelter. It is a self-contained, miniature biosphere, a mechanical and chemical recreation of the life-giving processes of an entire planet. The technology that accomplishes this is known as the Environmental Control and Life Support System, or ECLSS. It is the invisible, humming, and absolutely critical heart of any lunar settlement, a system built on the principle of radical efficiency and the near-perfect recycling of every precious molecule. On Earth, we live in an open system of immense scale. We breathe air, drink water, and discard waste, relying on the vastness of the planet's oceans, atmosphere, and ecosystems to process and replenish these resources. This is a luxury the moon does not afford. A lunar habitat is a closed loop, and its survival depends on its ability to reclaim and reuse everything. The most critical of these loops is water. Every drop of water in a lunar settlement is priceless. Whether it is initially brought from Earth or painstakingly extracted from ice deposits in polar craters, once inside the habitat, this initial supply must be guarded and recycled with near 100% efficiency. This cycle is the settlement's lifeblood, turning yesterday's waste into tomorrow's drinking water, a constant and vital process that underpins all other life support functions. The second critical element, breathable air, is directly tied to the water supply. The primary method for generating oxygen within the habitat is a process called electrolysis. Electricity, generated by the settlement's power systems, is passed through water. This electric current breaks the bonds of the water molecules, splitting them into their constituent parts, pure oxygen and hydrogen. The oxygen is vented into the habitat's atmosphere to maintain a breathable pressure, while the hydrogen is captured and stored. This makes a large, accessible reservoir of water ice not just a source of hydration, but the foundational resource for the very air the settlers breathe. In the long term, however, a settlement cannot rely solely on water for its oxygen. The ultimate goal is to live off the land, and the lunar regolith itself provides a near limitless, though technically challenging, source of oxygen. By weight, the lunar rock is approximately 45% oxygen, chemically bound to silicon and various metals in the form of oxides. Through a process like molten oxide electrolysis, this oxygen can be liberated. Raw regolith is heated in a reactor to extreme temperatures, over 1,600 degrees Celsius, until it melts into a molten slurry. An electric current is then passed through this liquid rock, which separates the oxygen atoms from the metal atoms. The oxygen gas is captured, and the molten metals, a useful byproduct, are drained away. This technology is a game changer, promising a future where a lunar settlement can produce vast quantities of breathable air directly from the ground beneath it, ensuring its long-term independence from Earth. Finally, the system must deal with what is produced by the crew: carbon dioxide. Every breath exhaled releases this gas, and in a closed environment, its concentration would quickly rise to toxic levels. The ECLSS continuously scrubs the carbon dioxide from the air, but it doesn't just store it. In a truly elegant chemical loop, systems like the Savatier process combine the captured carbon dioxide with the hydrogen left over from water electrolysis. This reaction produces two things: water and methane. The water is sent right back to the water processor to be recycled, meaning the very act of exhaling carbon dioxide ultimately helps to replenish the settlement's water supply. The methane can be stored for use as a basic rocket propellant. This is the beauty of a closed-loop system. The waste product of one process becomes the fuel for another. The constant, rhythmic hum of the ECLSS, its pumps, filters, and reactors, is the true soundtrack of lunar life. It is the sound of a small piece of Earth, a fragile technological bubble, sustaining itself against the silent, sterile backdrop of another world. Inside the meticulously engineered bubble of the lunar habitat, the air is pure, the water is clean, and the temperature is stable. The systems of life replicate the chemistry of Earth with tireless precision. But there is one fundamental force of nature that cannot be engineered, one constant that defines every moment of lunar existence: the unyielding pull of 1/6 of Earth's gravity. This is the single greatest and most transformative difference between the two worlds. It is an invisible tide that reshapes not only the way a settler moves and works, but the very biology of the human body itself. The initial experience of this low-gravity world is one of pure exhilaration. It is the realization of an ancient dream of flight. The body feels light, powerful, and unburdened. A simple step becomes a gentle, floating bound. A jump can carry a person several meters into the air, ending in a slow, graceful descent. Heavy equipment that would require a team to lift on Earth can be moved by a single person with relative ease. For the first days and weeks, life is a ballet of effortless motion, a newfound freedom from the tyranny of weight. But this initial paradise is deceptive. It masks a slow, silent, and insidious physiological rebellion. The human body is a machine forged in the crucible of Earth's gravity, and when that constant, lifelong resistance is removed, the machine begins to dismantle itself. The guiding principle of this disassembly is use it or lose it. On Earth, every moment, whether standing, walking, or simply sitting upright, is an act of defiance against gravity. This constant load-bearing stress sends a continuous signal to the musculoskeletal system to remain strong. In the 1/6 gravity of the Moon, that signal all but disappears. The large, powerful muscles of the legs, hips, and spine, which are responsible for posture and locomotion, are suddenly underemployed. With their primary reason for being drastically reduced, they begin to atrophy. The body, in its relentless efficiency, sees no reason to maintain such metabolically expensive tissue and begins to break it down. A similar and more dangerous process occurs in the skeleton. Bones are not static structures. They are dynamic, living tissues that constantly remodel themselves in response to physical stress. On the Moon, the load on the most critical bones, the femur, the hips, the vertebrae of the lower back, is reduced by over 80%. The body interprets this as a sign that these massively strong bones are now over-engineered for the environment. It begins a process of demineralization, leaching calcium from the skeleton back into the bloodstream. This results in a rapid loss of bone density at a rate of roughly 1 to 2% per month, a pace far exceeding even the most severe cases of osteoporosis on Earth. To combat this dual decay of muscle and bone, a settler's life would be governed by a rigorous and non-negotiable exercise regime. Several hours of every single day would be spent on specialized equipment, such as treadmills with harnesses that strap the user down to simulate weight, and advanced resistance machines designed to put the necessary stress back onto the body. Exercise on the Moon is not a choice for fitness. It is a medical necessity for survival. The cardiovascular system undergoes a similar adaptation. On Earth, the heart works constantly to pump blood uphill to the brain against the pull of gravity. On the Moon, this task becomes effortless. This causes a significant fluid shift in the body, as blood and other fluids that would normally pull in the legs move upwards into the torso and head. This leads to the characteristic puffy face and thin bird legs seen in astronauts. The body, sensing an excess of fluid in the upper body, reacts by reducing the total volume of blood plasma. The heart, now with less fluid to pump and less resistance to work against, begins to weaken and shrink, just like any other underused muscle. Perhaps the most surprising long-term effect of this fluid shift is a condition known as spaceflight-associated neuroocular syndrome, or SANS. The increased fluid pressure in the skull can physically alter the shape of the eyeball, flattening it slightly and pushing on the optic nerve. This can lead to significant vision problems, such as farsightedness, which may not be fully reversible upon a return to higher gravity. The very act of living in a low-gravity environment can permanently change the way a settler sees the world. These physiological changes are the backdrop to a new way of performing even the simplest of daily tasks. Walking becomes a loping, bouncing gait to maintain traction and forward momentum. Pouring a glass of water is a delicate act, as the liquid flows more slowly and can splash into large, floating globules. Dropping a tool doesn't result in a sharp, satisfying clatter, but a slow, silent descent and a gentle, muted tap. The world feels less grounded, less definite. Every physical interaction, from lifting a crate to turning a wrench, must be relearned, accounting for the fact that while weight is drastically reduced, mass, and therefore inertia, remains the same. To live on the moon is to live in a state of constant biological warfare against one's own body, a trade-off where the exhilarating freedom of movement is paid for with hours of grueling exercise and the acceptance of profound and perhaps permanent changes to one's own physiology. Life within the lunar habitat is a delicate, sustained miracle of technology. The life support systems that recycle every drop of water and every breath of air, the powerful exercise machines that fight the decay of muscle and bone, the very lights that hold the profound darkness at bay. All of these systems have one thing in common. They are all utterly dependent on a constant, uninterrupted flow of electrical power. Power is the master resource of a lunar settlement, the invisible foundation upon which all other aspects of survival are built. Providing this power in a world defined by extreme cycles of light and darkness is one of the most formidable engineering challenges that settlers will face. The central problem is rooted in the moon's slow rotation. A lunar day, from one sunrise to the next, is about 29.5 Earth days long. This means any given location on the lunar surface experiences roughly 14 Earth days of continuous, direct sunlight, followed by 14 Earth days of unbroken, deep cold night. This feast or famine cycle makes energy generation a far more complex issue than it is on Earth. During the long day, solar energy is an abundant and powerful resource. With no atmosphere to scatter or absorb the light, the sun's radiation is more intense and more reliable than anywhere on our own planet. The logical first step in powering settlement is to harvest this energy. This would be accomplished by deploying vast arrays of solar panels across the lunar landscape. These would not be the simple panels seen on terrestrial rooftops, but advanced, durable systems designed to withstand the abrasive lunar dust and the massive temperature swings. Robotic rovers would be tasked with their deployment and maintenance, methodically cleaning the dust from their surfaces to maintain peak efficiency. In certain strategic locations, such as the rims of craters at the lunar poles, it is possible to find areas of near-permanent sunlight. By building tall, vertical solar masts in these locations, a settlement could potentially harvest solar power almost continuously. For most of the moon, however, the settlers must confront the reality of the 336-hour night. Surviving this long darkness is a challenge of energy storage. The settlement must harvest enough excess energy during the day to power all its critical systems through 2 full weeks of night. The most straightforward solution is a massive bank of advanced batteries, similar to those used in electric vehicles and grid storage on Earth. But the scale required is immense. The sheer mass of batteries needed to sustain an entire habitat for weeks would be a significant logistical burden, requiring numerous heavy-lift rocket launches from Earth. A more sophisticated and sustainable solution lies in a technology known as regenerative fuel cells. This system creates a closed, rechargeable energy loop. During the sunlit day, a portion of the massive electrical surplus from the solar arrays is directed to an electrolyzer. This unit, just like the one used for life support, splits water into hydrogen and oxygen gas. These gases are then chilled and compressed into a liquid state and stored in super-insulated cryogenic tanks. They are, in effect, a battery in the form of stored chemical potential. When the sun finally sets and the long night begins, the process is reversed. The stored hydrogen and oxygen are fed into a fuel cell, where they are allowed to recombine chemically. This reaction produces electricity, heat, and a single byproduct, pure water. This water is then captured and stored, ready to be split again when the sun rises 2 weeks later. It is an elegant and highly efficient system that integrates seamlessly with the habitat's life support architecture. However, even with advanced storage, a system wholly dependent on solar power is vulnerable. A major technical failure with the arrays or storage system during the night could be catastrophic. For this reason, the most likely solution for a permanent settlement is a hybrid grid that includes the unwavering reliability of nuclear fission. Modern space-rated nuclear reactors, like those developed through NASA's Fission Surface Power Project, are nothing like the sprawling power plants of Earth. They are compact, about the size of a person, and designed for extreme safety and reliability. A single reactor can be transported to the moon, and once deployed, can provide a steady output of tens of kilowatts of power continuously for a decade or more without any need for refueling. This technology is a true enabler of lunar settlement. A nuclear reactor is entirely independent of sunlight, able to provide a constant baseline of power through the long lunar night. It can be deployed in permanently shadowed craters at the poles, allowing for robotic exploration and ice mining operations in areas where solar power is impossible. In the final analysis, the lunar power grid will be a fusion of these two philosophies. The vast solar fields will serve as the primary power source during the day, generating the immense energy required for industrial operations, scientific experiments, and charging the regenerative fuel cells. Meanwhile, a nuclear fission reactor will serve as the settlement's heart, providing a constant, non-negotiable stream of power to the most critical life support systems. This resilient, redundant network ensures that no matter how dark or cold it gets outside, the lights, and more importantly, the life, inside the lunar home will never go out. With a stable environment, a constant supply of power, and a mastery over the cycles of air and water, a lunar settlement becomes a viable outpost. But to become a true, self-sustaining home, it must solve the final and most fundamental challenge of human survival: the production of food. The logistics of relying on Earth for sustenance are simply unsustainable. The immense cost of launching provisions, the limited shelf life of packaged meals, and the sheer vulnerability of a supply line stretching 250,000 miles across space make it an impossibility for a permanent colony. Emergency rations and supplemental nutrients will always be a part of the pantry, but the daily diet of a lunar settler must be grown in situ, harvested from a farm on another world. This necessity gives rise to one of the most vital and complex parts of the habitat: the lunar greenhouse. This would be a dedicated module or a specially prepared section of a lava tube sealed off and transformed into an oasis of controlled agriculture. The very concept of a farm, however, must be redefined. There is no open field, no rich topsoil, no gentle rain or natural sunlight. The lunar regolith, being composed of sharp, sterile mineral fragments with no organic matter, is a poor medium for growing crops. Instead, lunar agriculture will be a soilless, high-tech endeavor, leveraging systems that provide the perfect combination of water, nutrients, and light with unparalleled efficiency. The most proven of these methods is hydroponics. In a hydroponic system, plants are grown with their roots suspended, not in soil, but directly in a circulating bath of nutrient-rich water. This allows for the precise delivery of all the minerals and elements a plant needs, eliminating the guesswork of traditional farming. Every drop of water is accounted for, recycled, and reused, making the system incredibly water efficient. a critical feature in an environment where water is a precious resource. An even more advanced technique, known as aeroponics, takes this a step further. Here, the plant roots are suspended in the air within a closed chamber and are periodically sprayed with a fine, nutrient-dense mist. This method uses even less water and provides the roots with superior oxygenation, often resulting in faster growth and higher yields. To maximize food production within the limited, valuable space of a habitat, these systems would be implemented in the form of vertical farms. Instead of sprawling fields, plants would be grown in stacked layers, reaching from floor to ceiling, with each level illuminated by arrays of custom-tuned light-emitting diodes, or LEDs. These lights would be programmed to provide the exact wavelength and intensity of light that each specific crop needs for optimal photosynthesis. Often glowing in surreal hues of pink and purple, the entire environment, from the temperature and humidity to the concentration of carbon dioxide in the air, would be precisely controlled by computers to create a year-round, perfect growing season. The selection of crops for this extraterrestrial farm would be a careful balancing act. The ideal lunar plants would be compact, fast-growing, nutritious, and have a high harvest index, meaning most of the plant's mass is edible. The first generation of crops would likely include leafy greens like lettuce and spinach, which grow quickly and provide essential vitamins. Radishes and carrots would offer variety and crunch. For carbohydrates and calories, settlers would rely on staples like potatoes, sweet potatoes, and a dwarf variety of wheat. Protein would come from legumes like soybeans and peas, which are versatile and can be processed into a variety of food products. Finally, for a taste of familiarity and a boost in morale, small, fast-fruiting plants like tomatoes and strawberries would be an essential part of the mix. In this perfectly closed system, nothing is wasted. The inedible parts of the plants, the stems, roots, and leaves, are not discarded. This biomass would be collected, heated, and decomposed in bioreactors, breaking it down into its constituent nutrients. These recycled nutrients would then be fed back into the hydroponic systems, completing the cycle. In a more advanced settlement, this principle of biomass recycling would extend to all organic waste, including human waste. After being completely sterilized and processed, the vital elements like nitrogen and phosphorus contained within it would be reclaimed and returned to the agricultural system. This is the final step in creating a truly self-sustaining biosphere, a miniature Earth where the cycles of growth and decay are managed and accelerated by technology. Beyond the purely practical necessity of providing calories and nutrients, the lunar greenhouse would serve another equally vital purpose. It would be a powerful psychological anchor for the settlers. In a world of sterile machinery, gray rock, and unyielding black sky, the greenhouse would be an explosion of vibrant life. The smell of damp earth and growing plants, the bright green of new leaves, the simple, tactile pleasure of tending to a living thing, all of these would be powerful sensory experiences, connecting the isolated crew to the biological world they left behind. The greenhouse would be more than just a farm. It would be a sanctuary, a therapeutic space, and a constant living reminder that even in the most hostile of environments, life, with enough ingenuity and care, can find a way to thrive. With the foundational challenges of survival met, the lunar settlement transforms from a mere shelter into a functioning outpost. The intricate systems of life support, power, and agriculture are the bedrock upon which the true purpose of the colony is built. For a lunar settlement to be sustainable in the long term, it must have a reason to exist beyond simple survival. It must be a place of productive work, a hub of scientific discovery and industrial output that offers a tangible return on the immense investment required to create it. The life of a settler, therefore, would be one of defined purpose, a highly structured existence divided between the essential labor of maintaining their world and the pioneering work of exploring it. The daily reality for the first generation of settlers would be dominated by the first category: maintenance and expansion. A lunar habitat is the most complex and high-stakes machine ever built, and it requires constant vigilance. A significant portion of the crew would be highly skilled technicians and engineers, their days spent monitoring the life support systems, calibrating the power grid, and maintaining the complex machinery of the lunar farm. They would be the plumbers, electricians, and mechanics of a new world, where a leaking pipe or a faulty circuit could have catastrophic consequences. Others would be roboticists, overseeing the autonomous systems that perform much of the exterior work, from cleaning solar panels to operating the 3D printing construction rovers. This work is not glamorous, but it is the most critical function of the settlement, ensuring that the fragile bubble of life remains secure. Beyond mere maintenance is the work of growth. The initial outpost is just a seed. The settlers would be tasked with its expansion, transforming it from a small base into a sprawling town. This involves scouting new locations for habitat modules, overseeing the robotic excavation and construction, and integrating new systems into the existing infrastructure. Every settler, regardless of their primary specialization, would need to be a capable generalist, able to fix a malfunctioning pump, troubleshoot a software glitch, or assist in assembling a new piece of the habitat. This constant, collaborative effort of sustaining and growing their home would forge a powerful sense of shared purpose and interdependence among the crew. While this foundational work keeps the settlement alive, it is the second category of labor, science and industry, that gives it its meaning. The moon is a scientific treasure trove, a natural laboratory that offers the chance to answer some of the most profound questions about our universe. Lunar geologists would be among the first true explorers, venturing out onto the surface to study the moon's pristine and ancient rocks. These samples are a physical record of the early solar system, untouched by the weathering and geological recycling that has erased this history on Earth. By studying them, we can gain unprecedented insight into the formation of our own planet and the violent processes that shaped our cosmic neighborhood. The moon is also the perfect platform for astronomy. The lack of an atmosphere means the view of the cosmos is perfectly clear, free from the twinkling and absorption that plagues ground-based telescopes on Earth. Huge optical telescopes built on the stable lunar surface could image distant exoplanets with stunning clarity. But the true prize for astronomers lies on the lunar far side. This hemisphere of the moon is permanently facing away from Earth, making it the most radio-quiet location in the inner solar system, completely shielded from the cacophony of radio, television, and satellite signals generated by our own civilization. Here, vast arrays of sensitive radio telescopes could be built, allowing astronomers to listen to the faint, primordial whispers from the dawn of the universe and to conduct the most comprehensive search for extraterrestrial intelligence, or SETI, ever attempted. Finally, there is the industrial work that will ultimately make the settlement economically viable and transform it into a gateway to the solar system. This begins with mining the most valuable lunar resource, water ice. In the permanently shadowed craters at the lunar poles, robotic miners would excavate this ancient ice. Once melted and purified, this water is not just for drinking. It can be split via electrolysis into hydrogen and oxygen, the primary components of the most powerful chemical rocket propellant. The moon would become a refueling station, allowing ships to launch from Earth with less fuel, top up their tanks at the moon, and then travel onward to Mars and beyond at a dramatically lower cost. The other key industrial task would be the extraction of a rare resource known as helium-3. This is a light, non-radioactive isotope of helium, which is incredibly scarce on Earth, but has been deposited in the top layer of the lunar regolith by billions of years of solar wind. Helium-3 is a potential fuel for clean, highly efficient nuclear fusion reactors of the future. The work would involve vast automated strip mining machines, scooping up the regolith and heating it to release the trapped gases, including the precious helium-3. This resource could one day be exported back to Earth, providing a new source of clean energy and establishing a true economic link between the two worlds. The work of a settler is thus a profound blend of the practical and the visionary, from the daily task of fixing a pump to the grand endeavor of fueling the future of human exploration. The lunar settlers have mastered their physical environment. Their habitat shields them, their machines provide for them, and their work gives them purpose. Yet, the greatest challenge of living on the moon may not be a technical one, but a deeply personal and psychological one. The human mind is a product of Earth, shaped by its rhythms, its sensory richness, and its scale. To live on the moon is to subject that mind to an environment for which it has no evolutionary context. It is to navigate a new and profound internal frontier, where the greatest battle is fought against the silent pressures of isolation, confinement, and a reality fundamentally alien to human experience. The first and most pervasive of these pressures is the disruption of time itself. The human body is synchronized to the 24-hour cycle of light and dark on Earth. This internal clock, our circadian rhythm, governs everything from our sleep patterns to our hormone levels and metabolism. On the moon, this fundamental rhythm of life is absent. The sun rises and then hangs in the black sky for 14 Earth days, bathing the landscape in continuous, unwavering light. This is followed by an equally long night of absolute darkness, a 2-week period where the only light is the distant glow of the sun and the reflected light from the Earth. To cope, the settlement would live on an artificial clock, most likely Coordinated Universal Time or UTC. The habitat's internal lighting system would cycle on a 24-hour schedule, brightening to simulate morning and dimming to simulate night, creating a bubble of terrestrial time. But the body would still be in conflict with the world outside. The knowledge that the sun has not moved for a week, or that it will not rise for another 10 days, creates a persistent sense of disconnection, a form of cosmic jet lag from which there is no escape. This can lead to chronic sleep disturbances, mood disorders, and a constant struggle to maintain a normal rhythm in a world that has none. This temporal disorientation is compounded by the dual realities of isolation and confinement. The settlers are isolated on a scale never before experienced in human history. They are not just far from home, they are physically and permanently separated from the entire terrestrial biosphere. The beautiful, swirling Earth in their sky is a constant, poignant reminder of every person, every animal, and every ecosystem they have left behind. This profound separation can create a sense of being an outsider to the human race, a spectator watching the world from an impossible distance. Paradoxically, this immense isolation is experienced within the tight confines of the habitat. While the lunar landscape outside is a vast open desert, it is a lethal one. Settlers would live with a constant pressed against the glass feeling. They can see for hundreds of kilometers in the clear vacuum, but they can never walk there freely. All outdoor activity is a complex, carefully planned, and risky expedition inside a bulky, life-sustaining spacesuit. Their true world is the interior of the habitat, a collection of rooms, labs, and tunnels. Life is lived indoors, in an entirely artificial environment, breathing the same recycled air and seeing the same faces, day after day. This can lead to a sense of monotony and claustrophobia, a feeling of being trapped in a sophisticated, life-giving prison. Underpinning all of this is the immense psychological weight of total dependence on technology. Every moment of a settler's life is mediated by machines. The constant, low hum of the life support system is the sound of their own survival. A flickering light or an unusual vibration from a pump is not a simple annoyance, but a potential existential threat. This creates a baseline of low-level chronic stress. It also fosters an absolute need for trust and social cohesion among the crew. An argument or a breakdown in communication is not just a social problem. In an environment where a single mistake can be fatal, it is a direct threat to the survival of the entire community. To mitigate these immense psychological pressures, a lunar settlement would need to be designed as much for the mind as for the body. Crew selection would be paramount, with candidates chosen for their exceptional emotional stability, resilience, and ability to work in teams under extreme stress. Life would be highly structured, with a clear schedule of work, mandatory exercise, and social activities to prevent idleness and foster community. And technology would offer an escape. Highly immersive virtual reality systems would be an essential tool for mental health, allowing a settler to spend a few hours walking through a perfect simulation of a forest on Earth, feeling a virtual breeze, and hearing the sounds of birds and flowing water. This would be a vital form of sensory therapy, a way to temporarily reconnect with the terrestrial world that is encoded in our very DNA. To thrive on the moon, a settler must not only be a brilliant scientist and a skilled engineer, but a master of their own internal world. A lunar settlement that can sustain the bodies and minds of its inhabitants has achieved a miracle of survival. But for this foothold in the cosmos to grow from a fragile outpost into a permanent, thriving city, it must achieve something more. It must become economically viable. The initial exploration of the moon will be funded by the governments of Earth, driven by scientific curiosity and national pride. But this model of dependence is finite. To ensure its long-term future, the settlement must learn to pay its own way. It must transition from being a costly scientific endeavor to a self-sufficient and ultimately profitable economic entity. The foundation of this new economy is a principle known as in-situ resource utilization, or ISRU, the art of living off the land on a planetary scale. The first and most important product in the lunar economic portfolio is not something that will be sent back to Earth, but something that will be sold in space itself: rocket propellant. The single greatest barrier to human expansion into the solar system is Earth's deep gravity well. The energy required to lift mass out of this well is immense, and according to the tyranny of the rocket equation, the vast majority of any rocket launched from Earth is simply the fuel needed to carry its own fuel. A permanent settlement on the moon, with access to the water ice deposits in the permanently shadowed craters of the poles, can completely upend this paradigm. Lunar ice miners, likely robotic, would excavate this frozen ancient water. Back at the settlement, this water would be melted, purified, and then fed into an electrolyzer. Using the abundant power from the settlement's grid, the water molecules would be split into their components: liquid oxygen and liquid hydrogen. These two elements, when combined, are the most powerful and efficient chemical rocket propellant known. The moon, with its 1/6 gravity, becomes an incredibly efficient place from which to launch this propellant into lunar orbit. The settlement effectively becomes a refueling station in the sky. This single capability revolutionizes space travel. A spaceship destined for Mars could launch from Earth with a minimal fuel load and a much larger payload of scientific equipment or habitat components. It would travel to a propellant depot orbiting the moon, top up its tanks with lunar-sourced fuel, and then depart for deep space. This makes missions more ambitious, more capable, and dramatically less expensive. The lunar settlement's first customers would be the space agencies of Earth, and its first major industry would be the production and sale of the fuel that powers humanity's next great leap into the solar system. With the local source of propellant secured, the next phase of the lunar economy focuses on building a local industrial base to reduce reliance on expensive imports from Earth. The same regolith that is used for construction and is mined for its trapped gases is also rich in metals. By weight, it contains significant amounts of silicon, aluminum, iron, and titanium, all bound up as oxides. The very same process of molten oxide electrolysis used to extract breathable oxygen from the regolith also produces a valuable byproduct, a stream of molten metals. This opens the door to lunar manufacturing. Instead of launching every spare part, every structural beam, and every tool from Earth, the settlers could begin to make them on-site. Advanced manufacturing techniques like three-dimensional metal printing would allow them to turn lunar-sourced metals into bespoke components. The purified silicon could be used to manufacture new solar cells, allowing the settlement to expand its own power grid without imports. This industrial self-sufficiency is a critical step, transforming the settlement from a passive consumer of Earth's goods into an active producer capable of maintaining and repairing itself. While propellant and manufactured goods serve the in-space economy, the long-term driver for a massive expansion of lunar industry would be the export of a unique, high-value resource back to Earth, helium-3. This light isotope of helium, rare on our planet, has been deposited into the surface of the moon by the solar wind for billions of years. Its value lies in its potential as a fuel for a future generation of clean, safe nuclear fusion reactors. The energy produced from helium-3 fusion would be immense, with virtually no radioactive waste. The economic incentive to secure a large, reliable supply of this fuel would be a powerful motivation for private industry to invest heavily in lunar infrastructure. This would involve large-scale, automated mining operations, scooping up vast quantities of regolith and processing it to extract the precious gas for shipment back to Earth. This would be the true maturation of the lunar economy, establishing a vital trade relationship that benefits both worlds. This robust industrial base creates a permanent, economically justified human presence on the moon. It solidifies the settlement's role not as a temporary scientific outpost, but as an essential logistical hub for the entire solar system and a vital economic partner for Earth. It is this economic foundation that allows the settlement to grow, to attract new residents, and to begin the complex process of evolving from a simple base into a true society. With the foundations of survival, industry, and mental fortitude established, the lunar settlement faces its next great evolutionary step. It must transition from being a highly specialized, mission-focused outpost into a true, functioning society. This is a challenge not of engineering or of science, but of sociology and politics. As the population grows from a few dozen specialists into a community of hundreds with diverse roles, backgrounds, and long-term intentions, the rigid, top-down command structure of an early base becomes unsustainable. The settlers must devise their own rules, forge their own identity, and begin the unprecedented experiment of creating humanity's first off-world culture. In its infancy, the settlement operates under a clear legal framework derived from Earth. The governing text is the Outer Space Treaty of 1967, a foundational document of international space law. This treaty establishes that the Moon is not subject to national appropriation by any country and is the province of all mankind. The early settlers are not colonists in a traditional sense. They are employees of national space agencies or private corporations, subject to the laws of their home nations and the specific codes of conduct of their mission. This structure works for a small, homogeneous group with a unified purpose, but it begins to fray as the settlement becomes more permanent and diverse. The first major challenge is the concept of law and order. How are disputes resolved? What happens in the case of a serious crime? Applying terrestrial law is fraught with complications. In a small, enclosed habitat, there is no escape for a potential criminal, and every other resident is a potential witness or victim. The very notion of a jury of one's peers takes on a new meaning when your peers are the only other 100 people in your entire world. The settlement would need to develop its own justice system, likely beginning with a form of appointed arbitration and evolving into a more formal legal code, a unique blend of terrestrial principles and new precedents set by the realities of lunar life. The question of property rights is equally complex. The Outer Space Treaty forbids national claims of sovereignty. But what about a private company that invests billions in developing a section of a lava tube, or an individual who builds their own habitat? The evolution of lunar property law will be one of the most critical factors in its future economic development. Beyond the formal structures of law, a unique lunar culture would inevitably begin to form, forged in the crucible of a shared, extraordinary experience. This culture would be built on the foundation of values dictated by the harsh realities of the environment. The most prized virtue would be competence. In a world where a single mistake, a misread sensor, a poorly sealed glove, can lead to disaster for everyone, technical skill and meticulous attention to detail would be held in the highest esteem. Alongside competence would be a deep commitment to the community. The radical interdependence of the settlers, their total reliance on one another for survival, would foster a collectivist mindset where the good of the group is paramount. Wastefulness would be seen as a serious social offense, and a culture of obsessive recycling, repair, and efficiency would permeate every aspect of daily life. New rituals and traditions would emerge, marking the passage of time in a world without seasons. There might be a settlement-wide celebration marking sunup, the return of the sun after the 2-week lunar night, a festival of light and energy. There could be solemn days of remembrance, honoring the sacrifices of those who were lost in the pioneering days. Art, music, and literature would emerge, reflecting the unique lunar experience, the profound silence, the stark beauty of the landscape, and the constant, awe-inspiring presence of the earth in the sky. The language itself would evolve, with a shared technical vocabulary giving way to new slang and idioms to describe concepts unique to their world. Ultimately, this would lead to a new identity. The first generation of settlers arrive as citizens of their nations on Earth, but as they live, work, and overcome challenges together, they would begin to see themselves as something else. They would be lunans, a new off-world branch of the human family tree. Their allegiance would be to the settlement, their shared home, and their perspective would be fundamentally different. For them, humanity is not a collection of competing nations on a globe, but a single, fragile, and distant civilization on a beautiful blue marble. This shift in perspective is perhaps the most significant cultural development of all. The lunar settlement is not just a collection of buildings and machines. It is a social laboratory, testing whether humanity, stripped of its terrestrial baggage, can create a resilient, cooperative, and forward-looking society on a new world. The success of this social experiment will determine whether the moon is simply a place we visit or the first step in our true cosmic diaspora, a lunar society with its own economy, laws, and budding culture has achieved a level of permanence that was once the domain of science fiction. It has become a true colony. But the ultimate test of any colony, the final measure of its success in establishing a new branch of civilization, is its ability to perpetuate itself. The question of whether humanity can not only survive on the moon, but also reproduce there, is perhaps the most profound and challenging of all. The birth of the first child on the moon would be a biological and ethical event of unprecedented significance, marking the true beginning of humanity as a multiplanetary species. This step, however, is a journey into a vast biological unknown. For all our knowledge of how an adult human body adapts to a low-gravity environment, we have virtually no data on how that environment would affect the delicate processes of conception, fetal development, and birth. On Earth, gravity is a constant, subtle influence on our biology from the moment of conception. It is a force that guides the development of our load-bearing structures, our cardiovascular system, and even our sense of balance. To create a new life in a world where that force is reduced to 1/6 of its normal strength is to conduct an experiment with the highest possible stakes. The questions are as numerous as they are profound. How would the 1/6 gravity environment affect the mobility of sperm or the process of implantation? During gestation, how would a fetus's musculoskeletal system develop without the constant gravitational load that signals bones and muscles to grow strong? Would the cardiovascular system mature properly without having to learn to pump blood against a significant gravitational gradient? The development of the inner ear's vestibular system, which gives us our sense of balance, is also calibrated to Earth's gravity. The first pregnancy on the moon would be an intensely monitored, high-risk medical journey, navigating a territory for which there are no maps. Should a pregnancy be carried to term successfully, the child born would be the first true lunar, a human being fundamentally different from any who had come before. Growing up in a 1/6 gravity environment, their body would develop in ways perfectly suited to that world. Without the compressive force of Earth's gravity, their spine might grow longer, making them taller than they would have been on Earth. Their bones would be lighter and less dense, and their muscles, particularly in the legs and back, would be significantly weaker, as they would be appropriately sized for the gentle pull of the moon. Their heart would be smaller and would work less vigorously, perfectly adapted to a life where pumping blood is an easier task. This perfect adaptation to their lunar home leads to the most significant and ethically complex consequence of off-world birth: the high probability that this child could never visit the homeworld of their ancestors. For a lunar, Earth would not be a welcoming place. It would be a gravity prison. The crushing force of 1G would be a torment to their body. Their heart might not be strong enough to pump blood effectively to their brain, leading to fainting or cardiovascular distress. Their muscles would struggle to support their own body weight, making movement a monumental effort. Their very bones, having never known a greater load, could be susceptible to fractures under the simple stress of walking. This raises a profound ethical dilemma. The decision by the first parents to have a child on the moon is an irrevocable choice made on behalf of an individual who cannot give their consent. It is a choice to create a human being who is, in a very real and physical sense, exiled from Earth. This child's universe would be defined by the walls of their habitat and the gray plains of the moon. The Earth for them would not be a lost home, but a giant, beautiful, and forever inaccessible planet in their sky, a place of myth and history, a museum they can see but never enter. Their identity would be forged in this unique context. They would be the first of a new kind, the true extraterrestrials of the human species, a bridge between two worlds, yet belonging fully to only one. The birth of the first healthy child on the moon would represent the point of no return in our cosmic journey. It would be the ultimate proof that our biology is not bound to a single planet. But it would also mark a new era of human responsibility. We would no longer be mere visitors or caretakers of a distant outpost. We would be the stewards of a new and distinct branch of our own species, obligated to ensure its health, its rights, and its future. This first lunar would be the living embodiment of our greatest achievement and a symbol of our most solemn duty. The first child born on the moon embodies the future of the settlement, a new generation for whom the Great Plains and black sky are the only home they have ever known. Their perspective is the ultimate expression of a profound psychological shift that affects every person who lives on the moon. It is a change centered on the most spectacular and ever-present object in their sky, the Earth. For a lunar settler, Earth is no longer the ground beneath their feet. It is a celestial body, a giant, living clock, and a constant, powerful source of perspective that fundamentally reshapes their relationship with their own species and their former home. Astronauts who have orbited the Earth for brief periods have described a cognitive shift known as the overview effect. Seeing the planet as a whole, a borderless sphere of life hanging in the void, has been reported to instill a deep sense of unity and an intense appreciation for its fragility. For a lunar settler, this is not a fleeting peak experience. It is the daily, unchanging reality. The Earth does not rise or set in the lunar sky. Due to the moon's tidal lock, it hangs in essentially the same position, day after day, week after week, a constant, silent companion. This constant presence transforms the planet into an object of intense study and art. From their unique vantage point, settlers can watch the grand theater of Earth's climate in real time. They can see entire weather systems form, the majestic swirl of a hurricane moving across an ocean, the flicker of lightning storms illuminating the night side of the planet, and the slow, seasonal creep of snow and ice across the continents. They would see the Earth not as a static map, but as a single, interconnected, breathing system. This view would undoubtedly inspire a new renaissance of art and philosophy, all centered on the dynamic beauty of the distant blue marble. From 250,000 miles away, the Earth's life-sustaining atmosphere, which seems so boundless from the ground, is revealed for what it truly is, an impossibly thin, delicate blue line haze clinging to the edge of a sphere. This perspective would instill a profound and visceral understanding of the planet's vulnerability. Settlers would be able to see large-scale environmental events with their own eyes, the pale plume of smoke from massive wildfires drifting across a continent, or the brown stain of a dust storm blowing out over the ocean. Living in a world of absolute resource conservation, where every drop of water and breath of air is recycled, they would look back at their former home and see a world of staggering and perhaps even reckless abundance. This would likely foster a deep and powerful environmental consciousness, a form of planetary stewardship felt most acutely by those who can no longer directly partake in the planet's biosphere. The constant view of Earth would also be a source of a new and unique form of homesickness. It is not the simple longing for a particular place or person, but a deep, species-level nostalgia for the very experience of being on a living world. The settlers would miss things they never before considered: the feeling of a breeze on their skin, the scent of rain on dry earth, the sound of leaves rustling in a forest. The simple freedom of walking outside under a blue sky without a helmet. The Earth in their sky would be a constant, beautiful, and sometimes painful reminder of all the sensory richness they have sacrificed. It represents a paradise that they can see and study in intricate detail, but to which they may never be able to return. Ultimately, This constant external perspective on their homeworld would redefine the settlers' sense of identity. On Earth, humanity is fractured into a complex tapestry of nations, cultures, and ideologies. From the moon, these divisions are invisible. The settler sees no borders, hears no arguments, and witnesses no conflicts. They see only a single, unified whole. Their primary identity would inevitably shift. They would see themselves not first as members of a particular country, but as members of a single human species, with lunar as their distinct cultural identifier. The tribal conflicts and political squabbles of Earth would seem distant and tragically small-minded when viewed from a world where cooperation is the only key to survival. This perspective, this humbling, unifying, and clarifying vision of our place in the cosmos, might be the most valuable resource the moon has to offer. It is a gift of wisdom sent back home from the first children of humanity to truly leave the nest. From our starting point on Earth, looking up at a distant silver disk, we have journeyed across the void. We have built a home beneath the lunar surface, learned to sustain our bodies with recycled air and water, and our minds with a new, profound perspective. We have forged a new economy, a new society, and have witnessed the birth of a new generation of humanity. But the story of the lunar settlement does not end here. The moon is not humanity's final destination. It is our first true starting point. It is the training ground, the logistical hub, and the cultural crucible where we will prepare for our expansion into the wider solar system. Living on the moon is like learning to swim in the shallows before attempting to cross the ocean. It is a world close enough to Earth that a rescue mission or a critical supply run is only a 3-day journey away. Yet it is a world so completely alien that it forces us to solve every major challenge of off-world survival. It is here, in our own celestial backyard, that we will perfect the technologies and strategies needed for more ambitious journeys. The closed-loop life support systems, the fission power generators, the subterranean habitats, and the low-gravity agriculture, every system mastered on the moon, is a direct blueprint for a future settlement on Mars. A mistake on the moon is a crisis. A similar mistake on Mars, a planet that is months or even years away from help, is a catastrophe. The moon is where we will learn, adapt, and earn our license to explore the rest of the cosmos. It is also a proving ground for the human spirit. The moon is where we will gather the first long-term data on how human beings cope, physically and psychologically, with life on another world. We will learn what kind of people are best suited for the immense stress of off-world life, what social structures are most resilient, and what support is needed to keep a small, isolated community healthy and productive. The lessons learned from the first lunar society will be the foundation for every human community that follows, on any planet or moon we may one day call home. Beyond this role as a training ground, the lunar settlement will become the most critical piece of infrastructure in the future of space exploration, a logistical gateway to the solar system. Its industrial base, founded on the production of rocket propellant from polar ice, transforms the economics of deep space travel. The moon becomes the port of call for any major interplanetary mission. An ambitious voyage to Mars will no longer depart from the deep gravity well of Earth. Instead, the components of the great exploration vessel will be launched to lunar orbit. The ship will be assembled there, and its tanks will be filled with powerful, inexpensive, lunar-sourced fuel. The crew, already acclimated to a low-gravity environment at the lunar settlement, will board this vessel and begin their long journey not from their homeworld, but from its first permanent off-world harbor. The industrial capacity of the moon will support these missions in other ways, manufacturing tools, spare parts, and even structural components from local resources, further reducing the mass that must be arduously lifted from Earth. In time, the moon becomes the anchor of a new, self-sustaining in-space economy, a hub of commerce and technology that supports human activity across the solar system. From the moon, we will go to Mars. Using the lessons and resources from both the moon and Mars, we will venture further, to the asteroid belt and to the ocean moons of the outer planets. Our journey ends where it began, but with our perspective forever changed. We started by looking up at the moon as a symbol of our dreams. We end by standing on the moon, looking back at the Earth as a symbol of our origin, and looking out at the stars as a map of our destiny. The great lesson of the lunar settlement is that in leaving our home, we come to understand it, and ourselves, more deeply than ever before. It teaches us that the immense void is not to be feared, but to be navigated with courage, ingenuity, and a profound appreciation for the fragile, living world we carry in our memory. The settlement on the moon is not just a triumph of technology, but a testament to the relentless, exploratory spirit that defines what it is to be human. The journey continues, always calmly, always at the rhythm of the universe.